has all of this data. Johannes Kepler is on a mission from God in his world, and he goes, knocks on the door. Excuse me, I'm here to save the world. I need, gentlemen, can we close the laptops, please? Knocks on the door. I'm on a mission from God. I need the data. Dane's family says, no, really, we want to hold on to it. Dylan Anderson looked it up. There's actually 15 volumes of data. So Kepler's in a moral quandary. Do I'm on a mission from God? Do I do that? Or do I have ethics and not steal it?
Of course he still stole it.
Of course he steals it, right? Because he's advancing science over ethics. So one of the great laws of planetary motion were developed from data that was stolen. So he storms the castle wall, gets the data, goes back to Germany. So he's trying to figure this out. So the first thing to really make sense of this, there's a couple of things you need to understand so you can understand what Kepler was dealing with, okay? So the first thing we need to figure out is that if you're looking down on top of the North Pole, okay? So here's Santa's workshop. You're looking down on top of the North Pole. Does the Earth spin clockwise or counterclockwise as viewed from the North Pole? Clockwise? Counterclockwise?
Doesn't. Counterclockwise.
Well, let's settle this. Okay? So this is looking down from on top of the North Pole. Okay, so there's the North Pole. So let's say that Ava is the sun. Okay? Ava is the sun. And here's a reindeer here in Mays, Kansas. Okay? Ava's the sun. So if the reindeer is here and Ava's the sun, what time of day is it?
Noon.
Noon. Why?
It's directly above.
Yeah, Ava would be directly overhead. So if you're here, boom, the sun's directly over here. That's like noon. Okay? If Ava's over here on the opposite side, midnight, right? Cool. So you got midnight, you got noon. So let's say you think the Earth spins clockwise like this, okay? So here you are in Mays, America. So you're here, and obviously not to scale, where this is one really big reindeer, and you're going to come around here like this, and then you're going to be able to see Ava as it comes around like this. Now, if the Earth spins clockwise, you're going to be looking towards California to see the sunrise.
East. West. That's what I said, west.
California is west of us. So if the Earth spins clockwise, the sun would rise in the west.
That's wrong.
If the Earth spins counterclockwise, and you come around like this, you're looking to the east to see the sunrise. So the first thing we know is that our Earth, viewed from on top, spins counterclockwise. Okay? Got that? All right. Now we need to talk about our moon, which is kind of cool that we have one. Stabilizes our orbit, gives us tides. So this is not to scale. All of these diagrams are so not to scale. Here's the sun, here's the Earth. To give you some perspective on, like, if this were to scale, if this was the actual size of the Earth, and this is about to scale about the size of the moon relative to the Earth. And I said, you know, to scale, how far would the moon be? The moon, to this scale, would basically be along the back of the room. Okay? To scale, that's how far the moon would be. Okay? That isn't the sun, that's just to the moon. Okay? Gary said, oh, the moon's fairly close. No, the moon's really not. So you could put all of the planets between us and the moon. Jupiter, Saturn, even the giant planets. you could put, if you stack them side by side by side, you could put them in between the Earth and the Moon, okay? We think it's fairly close, it's really not. It's not way out. So, that's why I say these diagrams are so not to scale, but you get the idea.
How can we see it so much more clearly than we can like the other planets?
Because it's still relatively closer than the other planets. Yeah. Okay, so here's the sun, here's the Earth. This is looking down. You have to understand the perspective. This is looking down on top of the Earth. Earth is spinning counterclockwise. So if you're right here, what time of day is it? Noon, right? Sun's directly overhead. If you're over here, midnight. What's that? So there's the dark side of the Earth. So if you're right here on this border between darkness and light, what time of day is it, roughly?
Nice. Dusk?
Dusk?
Or dawn?
Dusk?
6 p.m.
Didn't see the sunset, right? It's going to be sunset.
I don't think 6 p.m.
Okay? And that varies depending upon the time of year, right? Well, that's going to be sunset. Because you would be looking this direction to seeing the sun go down, right? So you would be looking across the horizon to see the sunset. So then if you're over here, what's going to happen? That's going to be sunrise. Okay? So we got midnight, noon, sunrise, sunset. Got it. Good. Looking down from on top. Now we're going to introduce our moon. So the moon can be at 4 positions. A, B, C, and D. Okay? Again, horribly not to scale. I can't emphasize how bad out of scale this drawing is. Here's the question. Where is the moon during a full moon? A, B, C, or D? Everybody cool with A? Why?
Because the light is reflected off of it.
Okay? So, would you agree that the dark side of the moon is going to be on the opposite side of us at that time? Right? If you were at D, okay, there's 2 reasons why you couldn't see the moon. What's one reason? Number 1, you're looking at the sun directly overhead. That's problematic. Okay? What else you got?
It's the dark side.
Yeah, you're looking at the dark side of the moon. Okay? So this would be a new moon, right? Can't see it for 2 reasons. You're staring into the sun, and even if you could see the moon, you're looking at the dark side of the moon. Okay? Now listen to me very carefully on the next question I'm going to ask. Okay? In about 2 weeks, we're going to have a full moon. So if I want to plan ahead, so I want us all to get together to watch a full moon rise. Okay, so listen to me very carefully. I want to watch a full moon rise. What time of day on Earth would a full moon rise? You got 4 options. Noon, midnight, sunrise, sunset.
Wait, full moon rising?
I want to see a full moon rise.
Sunset.
Sunrise, sunset, noon, midnight. How many vote noon? Thank God none of you voted noon. Why?
Because the sun is out. You can't
Well, that and where are you at?
you'd be looking.
You're on the other side of the earth. You couldn't see the full moon if you tried. Okay? What about midnight?
It's already good.
Oh, the moon.
Where's the moon going to be?
In the middle of the
Directly overhead. So we've eliminated noon and midnight. Leaves the sunrise and sunset. What do you got? Sunset. Why?
Because the sun is rising, not the moon.
The sun disappears.
Because if you're here,
The sun
okay?
can't rise.
So imagine this is the earth, okay? And I'm the full moon, Ava is the sun, okay? So the earth is going to spin counterclockwise like this. So as this comes around, here you are. This is noon, you're directly overhead. Midnight, I'm the moon. I'm getting sunlight from Ava, right? So as this goes around, when I hit this point right here, I would look towards the west, and I would see Ava setting. I would look towards the east, and I would see me rising. Okay? So when it's a full moon, it rises at sunset, it sets at sunrise. Okay? Now, when the moon is over here in this region, okay? Let me ask you this. Is it possible to see the moon during the day?
Yes. Yes.
Absolutely you can. So let's say the moon's over here. Okay? And there's the dark side of the moon. The moon's over here. The moon's over here. When is the moon going to rise?
Noon.
Why?
It's like one cycle before it, so you're still turning into it.
Yeah. So if I'm here, I would look in this direction and I would see the moon rising. But how much of the moon can you see? Yeah, well, what they call a quarter, right? So you can only see that lit quarter. So this is why sometimes the moon is visible during the day. If the moon's over here, there's the dark side of the moon. If the moon's over there, when would the moon rise? Midnight. Okay? But then it would set at noon. Okay? So this is why it's possible to see the moon during the day. Okay? Got that? Cool. New diagram. Sun,
Why
Okay.
are there two suns?
Earth.
We're inside the
What are the two interior planets?
Mercury and Venus.
Mercury and Venus. What? It's Mercury. Oh, speaking of chemistry, happy mole day. Why is today mole day?
Because it's 10:23.
Yeah.
Because
It's 10:23.
Avocados.
Okay. Avogadro's number is
6.02.
6.02 times 10 to the
23rd.
23rd. So it's mole day. So
Oh my goodness, it's mole day.
okay. So here's the question. Is it possible for you to ever see a full Venus or full Mercury?
Oh. No.
No.
They're never behind us.
Because if they were both full, the moon would cover the earth.
Because it'd have to be on the other side from the sun.
Okay,
They can
let's say Mercury and Venus are here,
Because they're not rotating around them.
Okay.
They're just not.
right? Mercury and Venus are in line with the Earth,
Really?
okay? Let's just say. So first off, what would you be looking at if you're trying to see them?
The sun.
The sun, and you'd also be looking at the dark side. Can't see them though. Okay, problematic. Instead of looking at the sun, give me some Mercury. Now, what if they were over here? The sun's still in the way, but you could at least see the lit side of them, but the sun's in the way. Small problem. Now, Mercury and Venus are known as the morning and evening planets. Why?
Because you can see them in the morning and evening.
Ah, you can see them in the morning and the evening. Why? So if Mercury or Venus are over in this region, so there's the Earth. Mercury and Venus are on this side of their orbit. What time of day would you see them?
In the morning.
Sunrise, sunset? Sunrise. Because you would be looking this way and seeing them right before you saw the sun. So as I come around, okay, so let's say Ava's the sun, okay, and Jonathan is Venus. So as I come around, I would see Jonathan and then I would see Ava. So I would see Jonathan a little bit before I saw Ava. Now, if they're over on this side, what's going to happen? So I'm going to come around like this. I'm going to not be able to see Ava, but then I've got Ryan. So then I'd be able to see Ryan on this side. So you can only see Mercury and Venus during the morning or during the evening. Okay, that's what they're referred to as those types of stars. Now, this is an option. So let's say it's spring and you're going to prom. And it's midnight. And you're contemplating how smart your date is. It's midnight. It's midnight. You walk out and you pick a random bright star. And you go, oh, look, there's the planet Venus. It's midnight. You pick a star and go, oh, there's Venus overhead. And your date goes, oh, yeah, I see it. That's cool. Does your date understand astronomy?
No, stupid.
Now, but here's the downside. If your date does understand astronomy,
You don't have a
you
date.
look like an idiot. Okay, because she's gonna go, dude, really? It's midnight and you think Venus is out there at midnight? You don't understand astronomy. You're a schmuck. So just be careful about that, because that can boom around and come back to you real fast. I'm just saying. Okay. Now, let's talk about what Kepler had to deal with. So Kepler is said to have waged war on Mars. So
Who said that?
here's the sun, Kepler did. That was the statement. So what do you know about Mars? It's the red planet.
It's dark.
Named after the god.
Is it outside of our orbit?
Yeah.
Now, what's a simple observation you could do to prove that Mars is outside of our orbit?
It takes longer to revolve the sun. Like when we're
Nah, that takes a while.
It's on the other side of Venus.
You can see it during the nighttime right above you.
Yeah, you can see it at midnight, right?
You gotta say it
If you can see any planet at midnight, where does it have to be?
behind us.
Behind us. Now, in light of that, if you have that vision at all, the whole idea of the Earth being the center right away negates Mercury and Venus, because you can never see a full Mercury or Venus. Because right away you're going, well, if they did orbit us, why could we never see a full one of those like we saw the moon or Mars? So right away it's like, something's weird with Mercury and Venus because we can't see a full one of those. So this is going to be important. At some point, you could see a full Mars. It would rise at set at sunrise. And you would see the full Mars. Now, Kepler had to keep track of two things. He had to keep track of how long it took for them to go around, and he had to keep track of distance. Now, Kepler had a whole bunch of things stacked against him. He didn't have a calculator. He didn't have Oreo cookies. He didn't have the internet. He was basically working alone. And he had 15 volumes of data to go through, okay? The other thing that he ran into was that how you judge the position of Mars. Because it isn't like you can take a telescope and look at Mars and go, oh, that's clearly 2.58 times 10 to the 8th meters away. Got it, okay?
Just like measuring an electron.
Oh, exactly, but just with a much bigger scale of distance.
Right.
Okay. So that became a problem. It's like he could make the observations, he could see it, but how do you judge distance? And this makes it even more complicated. Number one, his platform that he's viewing it from is the Earth, which isn't stationary. It's moving. Not only is it moving, it's spinning on its axis. Not only is it spinning on its axis, the axis is tilted. And the Earth actually moves in an elliptical orbit slightly, which means that it's always speeding up or slowing down. So he was trying to judge positions of things where everything is moving. So let me give you an idea of the trouble that he had to go through, okay? So here's Mars, and let's say that we'll make it something simple. Let's say back behind Mars is the three stars that make up the belt of Orion, okay? Very famous winter constellation. So he would look on Earth, midnight, boom, he's looking, he's seeing Mars in the constellation Orion. So that would be like me looking at Isaac Bruce and going, oh, Isaac is in the constellation Blue Shirt, okay? Because that's what I had to judge. I can only judge Isaac's position relative to what's in the back behind it, okay? So at some point, Mars is going to go all the way around, and it's going to end up back at that same point. One lap, okay? Which takes a little bit less than 2 years for Mars, okay? So if you like birthdays, don't go to Mars. You only get a birthday like every 2 years, okay? But here's the problem. The Earth takes 1 year to go around. It takes Mars about 1.88 years. So what that means is that when Mars gets back to that same point, the Earth might be over here. So even though the Earth has changed and Mars is back to its same point, now when you're trying to view Mars, where is it not going to be? In that same constellation. So that would be like me. I'm viewing Isaac right now. He's in the constellation Blue Shirt. But if I'm over here, even though Isaac hasn't moved, now he's in the constellation Crab Poster. He's in the exact same position, he hasn't moved. But from my perspective, it looks completely different. So now he's back, but how do I compensate for that? How do I know that it looks completely different, but yet he's back in that same point? If I'm over there, he's going to look like he's in like the constellation Purple Shirt. So how do you do that? So what he did, and Kepler used the tools that he had brilliantly. So to figure out the orbit, what he would do, he would basically like triangulate points. So he would say, okay, based upon this position of Earth and where it is, he could say it's on this line. Then 6 months later, Earth is over here, because that's how long it would take for the Earth to move around to the other side. Then he could look at it and go, okay, then it's at that point. So then he could kind of work backwards and get an idea of where that orbit is. So this is why Kepler had to have years and decades worth of data. You're not going to walk out in the night sky and go get a telescope, even with a modern telescope. Oh yeah, there's Mercury. Got it. Look at it. Okay, yeah, well, I know exactly how far it is. It isn't like golf where you have like a range finder. It's like, oh, how far is Mercury? Oh, we'll just give it a look. Oh, okay, well, that's how far away it is. Okay? It's horrible. They're very, very difficult computations. So that gives you an idea of what he had to deal with. So this is why he picked Mars. Because number one, it's the closest outside planet. Also, he could always get some data on Mars, except when. It's the only time he would not be able to see Mars.
When the Earth is directly across from
When it's directly opposite the sun. Okay? That's the only time he would not be able to get any data at all. Even if Mars is here, he'd be able to see it right before like sunrise. Or if Mars is over here, he'd be able to see it right after sunset. So he'd always be able to get some data, except for those small bits of time when it was directly behind the sun. Okay? Cool with that. So, let's talk about Kepler's 3 laws. Notice these are laws. These aren't suggestions. These aren't, well, we think this happens. Okay? These are laws. So, let me hand this out. Stand up, take a stretch, stop that camera. This is just a summary